Our second unit is on dynamics. You guys may know the word dynamics from like other settings. For example, dynamics in music. Any of you guys musicians? What does it refer to in music? Yeah, loud and soft. Basically, it's your volume. Dynamics would be a good way of using that. In other settings, like you could talk about, like, say, group dynamics, which would be like interactions of how you get along. Okay, so none of those are the definition for physics, though. Dynamics really has to do very similarly with kinematics. Kinematics describes the how objects move. Dynamics talks about why objects move. Does that make sense? So I could drop this pen here, and we could figure out things like velocity, acceleration, distance, time. That's the how it moved. But we also want to start understanding the root causes for why things moved. Why did the pen fall? Which is a force. And the force of gravity caused the pen to drop to the floor. Does that make sense? So there's actually going to be a lot of overlap, a lot of similarities. The formulas that we learned in the kinematics unit, we still need to be able to use in the dynamics unit. It's not like it's going to be like a one-off and we never use them again. We're actually going to use them quite regularly. Does that make sense? So please don't think that you can just forget everything we've previously learned. Okay. I threw one diagram up here that I hope kind of relates to the beginning. It's a tug-of-war match. Often we're going to talk in dynamics about forces in play that are going to be like pushing and pulling. Let me get to some of my notes here. You guys can read this. Dynamics basically studies the effects of forces. Kinematics studies the actual motion itself. Do you guys know who Newton was? Sir Isaac Newton? Yeah. I've got a slide on him on the next slide here. I want to talk a bit about him and then come back. Well, let me start. I'm going way out of order here. Okay, sorry. I'll stick with the first slide here. Sir Isaac Newton was probably one of the most influential physicists, and we actually have named an entire branch of physics kind of after him. We either call it classical physics, or sometimes we call it Newtonian physics. And basically that's what we're doing right now. We're doing what would be considered Newtonian physics. We're discussing like everyday life objects. So, I mean, an F-18 fighter is an everyday life object. You know, like reasonable size, reasonable speed. Eventually, if you go far enough in physics, we can start talking about some of the more obscure things. Like, what if the thing in question was not a plane, but an electron? Well, now it's like the smallest unit of matter we have. That kind of changes things. Or what if it wasn't moving at 100 meters per second? What if it was moving the speed of light? That changes things. Maybe you guys have heard the term quantum physics. Okay, quantum physics has to do with either the very large or the very small at like crazy speeds. Okay, but classical physics has to do with things that are like more normal everyday stuff. Does that make sense? So as long as the objects are not microscopic like subatomic particles, it's going to be Newtonian. My next two slides, just so you know, I'm not testing you on Galileo or Newton.
Mr. Bonnet, you have a call on line 1. Mr. Bonnet,
But
you have a call on line 1.
I think it's fairly worthwhile to know a bit about the past so that we know kind of how physics evolved. Probably the two most important names are Galileo and Newton. So let me just point out some of the highlights. Galileo, he's very famously known for proving that heavier things do not fall faster. I think I told you guys this story before. He went to the top of the Leaning Tower of Pisa. He dropped two cannonballs, one each of different sizes. Hopefully no one was underneath the cannonballs because they fell a long ways. And what they discovered is that the two cannonballs, they hit the ground at the same time, thereby proving that heavier things do not fall faster. Does that make sense? Okay. Some other things that he did. He built a telescope, which in 1609, by the way, is crazy. They didn't have that technology that we did back then. So like for him to build his own telescope back in 1609 is impressive. He wasn't the only one, by the way. There were other people who did this sort of thing. But he discovered some things like mountains on the moon, moons orbiting Jupiter, and dark spots or sunspots on the sun. Here's where this became kind of controversial. I've told you the story. He then believed that the Earth was not the center of the universe. Previously, the Catholic Church believed that the Earth was at the center of the universe and the sun went around the Earth. Have you guys heard this story before? So he opposed the Catholic Church. He could not prove his theories, and so they locked him up for the rest of his life under house arrest. One of the most brilliant minds probably ever, but he had to be basically in jail. Like, it wasn't probably jail, but like he couldn't leave his home, and he was branded a heretic. He was right though. And so I often use that story with you guys because I don't care that you have the right answer. What's more important to me is that you show me that you have the right answer. That's what's way more important. It also helps when I'm marking your test because if you make a dumb mistake, I can still give you a lot of marks if you just did one little thing wrong. So. One more thing I thought was kind of cool here. In 1992, they finally overturned his conviction.
They finally
Apologized. John Paul II. I put a little note on there. It took him long enough, eh? Oh, it's like finally the Catholic Church decided to agree. Okay, you're right. The Earth is not the center of the universe. Isn't that crazy? 1992, they finally officially apologized. So that's Galileo. Sir Isaac Newton then comes after Galileo. This is crazy coincidence. He was born the year Galileo died. So it's like they exactly overlapped with each other. He's known for going to Cambridge, and I was reading up on him. He was taught a lot of the Aristotle theories about how physics worked, which were things like heavier objects fall faster, the sun is not the center of the universe. And Newton actually, I believe I read somewhere, he wanted to drop out of school, like he hated school, because he thought they were teaching it wrong, I guess. And so he started researching things on his own and looked into other people, like Copernicus, Kepler, and Galileo, who were like the heretics of the time. They were like the radicals who had these crazy new ideas, if that makes sense. And so like the establishment was teaching one thing, and he kind of wanted to buck the establishment, if that makes sense. Which I'm glad he did, obviously, because he was right. He's also known as being one of the founders of calculus. He's most famous, at least for our course right now, of what are his 3 laws of motion. And if you guys have looked at the schedule for the next couple of days, the next 3 classes after this, each day we're going to talk about his laws of motion. Okay, so that's where we're going the next little while. Side note, he actually had this huge rivalry with a guy named Robert Hooke, which maybe you guys have heard his name before. We might have talked about him in Science 10 class.
An idea of atom?
He did a lot of things. He worked in light and optics. He also made microscopes. Robert Hooke was known for that. Anyways, they had huge battles. They accused each other of plagiarism all the time. Like they kept saying that you're stealing my idea, you're stealing my idea. Anyways, it sounded like it was an intense rivalry. I thought this was interesting. When he did his book, his most famous book, Principia Mathematica. Yeah, there it is. He didn't put calculus in it. Even though he had invented calculus, he chose not to put calculus in it because he was afraid his rivals would steal his ideas. Sounds crazy to me, but like he didn't want to like publish his famous calculus ideas. Anyways, and then last thing, he's actually was eventually knighted for his work and stuff like that. So, anyways, just some basic background information on these 2 guys. Newton is the important guy I want to talk about though, because Newton had a unit named after him. Have you guys heard of the term a Newton? Yeah, Newton refers to the unit we use for forces. So that's where I want to start basically now. This is where kind of we want to start now. So don't feel like you got to memorize that old stuff on there. I'm not testing you on Newton's birthday or anything. Yeah, no. So hopefully you guys have heard this before. A force is either a push or a pull. Have you guys heard that definition at one point in your lives? That's like the grade 10 definition. I'd like to give you a more sophisticated definition. Forces are interactions which change the motion of an object. That's a bit more technical. Let me say I hold my pen right here. Is it currently moving?
No.
Okay, let's say I let go of it. I won't. I don't want to break my pen. It's going to fall, right? Why? The force of gravity. Yeah. One more thing, though. What force did... Gravity was always acting on the pen. What force changed?
You let go.
Yeah. There was also the force of me holding the pen up. Does that make sense? And because I let go of the pen, I stopped applying force on the pen, and that caused the motion of the object to change. So like I said before, we really focused in the past on like the how things moved, so we could calculate the distance, velocity, time, all that stuff. Now our goal is to figure out, well, why did it move? What forces changed, causing objects to then move themselves? Makes sense? So I highlighted a few important words. If an object's motion is changing, there better be some sort of velocity. And if you're somehow changing a velocity, there better be some sort of acceleration. Does that make sense so far? So I just want to make sure that comment is clear. If you're going to change the motion of an object, to change the motion of an object, you need to change a velocity of an object. Does that make sense? To change the velocity of an object, therefore you need to have an acceleration. So one of the things we're going to work on here is that a force means there must be an acceleration. Okay. One of the things we often then do, because we're working with accelerations and forces, they're actually vectors. And so we can draw vector arrows pointing in directions that things are occurring. I found this picture online. This is an example of a car. A car could have a motor that's trying to pull it this way. But is that the only force acting on a vehicle? Well, no, there's other forces. For example, I actually don't know what RR stands for, but would drag make sense as a force? Drag force being something that's going to slow the car down slightly, like air resistance? No. Even here, there's an arrow pointing for gravity. Hopefully that makes sense as a force. We'll talk about normal force a little later. Lift force, I'm imagining, is probably like air that's kind of getting underneath a little bit, kind of like what makes an airplane actually have lift. We don't really focus on lift in this course. I have no idea what RR was supposed to mean, but what was that? It might be, but I have a feeling that's what they were going for with drag. So, anyways. The term I want to introduce is it's called the free body diagram. We're going to be drawing a lot of these sorts of things. So let me give you some more examples. Let's draw a free body diagram for a person standing still. This may sound ridiculous. So here is a person standing still. What forces are currently acting on that person? Well, for sure gravity, right? Which way would then gravity act? Down. Yeah, okay, so that makes sense. The gravity would act down. So let's draw an arrow down and call it F. And then small g. The force of gravity, yeah, sure. Is that the only force acting on you? Probably not, but you are standing still, so is anything making you go side to side? Okay, well then why don't you plummet through the floor? Because if you look at this diagram right here, if the only force acting on you is gravity, you would then be a projectile, meaning that you would basically keep plummeting down and down and down. So something must be going the other direction.
You're like standing up though.
Okay, so what is pushing you back up? Yes. Say that louder. The floor. The floor is actually pushing you back up. Does that make sense? No. I mean, if the floor wasn't pushing you back up, you would plummet for forever, right? So we actually have a term for that. It's called the normal force. And I've got that on my next slide. But gravity is often opposed in the opposite direction by what's called Fn. And the best way of describing that is hopefully like what I was saying there. The floor is actually holding you up. Just like with this pencil right here. Gravity's trying to pull this pencil down to the ground, but why isn't it plummeting? Because I'm holding it. That holding it would be considered what's called a normal force. That's what we refer to it as. As soon as I let go of that normal force, well then my pen starts to move. Does that make sense? So that's my next slide here. Normal force is a force perpendicular to a common surface. It would be the force keeping the object from falling. There's a lot of normal force in the world then, isn't there? Because everywhere that gravity exists, if the object is not moving, there must be a normal force keeping it up. Now, in a lot of examples, that could be like a table or a surface. Okay. What if you were, say, parachuting? Well, but the parachute itself would have a normal force on the air trying to pull you back up, kind of. Does that make sense? Like, gravity's pulling you down, but the parachute is actually undergoing a normal force, which is then trying to prevent you from free falling. Now, in that example here, let me just draw a quick picture here. Not great at drawing. Person, backpack, parachute. If the gravitational force is greater than the normal force, what would happen? You would fall, right? So chances are what happens if we draw vector arrows is that the normal force would be like, say, 20 newtons, but the gravitational force would be 30 newtons. Does that make sense? And so if one is bigger than the other, then you can kind of keep falling.
So normal force is like the opposition of gravity?
That's a good way of putting it, yeah. Normal force is usually opposing gravity. I mean, it's something that's keeping something from falling, right? Like my hand right now is undergoing normal force. When I have a pen on my hand, is there a lot of stress on my body? Okay, but what happens if I were trying to hold up something really heavy? Would it not make sense that I was actually exerting some effort? Like I had to use some force to lift something quite heavy? Well, that's normal force because I'm trying to oppose gravity. Does that make sense? So, another term I need you guys to know is net force, which kind of is, I can use this example to describe here. If gravity's pulling you down at 30, but the parachute is trying to hold you up at 20, how much net force do you have? 10. Yeah, I gotta be more specific though. It would be 10 newtons down.
Oh, so it's like a displacement?
Yeah, I mean, it's not actually a displacement, but it's a vector again, right? Where you have to have a direction to it. So a net force would be the sum of all forces. Okay. Here's an important line here. Often a net force is 0. As you sit on your chair, there are forces working on you. Gravity's trying to pull you down. The chair is pushing you back up so that you don't plummet through the floor. Does that make sense? What would happen if the stool were to break?
Well, you would.
Then you'd fall on your butt, right? Well, in that example there, then the chair was not doing its job properly. It's internal forces that keep the stool together. If they start to break down, you get where I'm going with this here? Then that normal force that it's trying to push back up with would not work and it would collapse. And so, I mean, imagine that you're, I don't know, I guess an engineer would be a good example. You're trying to build a bridge. You have to account for things like, well, gravity is going to be trying to pull all these cars down, so I need to make sure that this bridge is capable of holding them up. Does that make sense? Okay, side note here. Can the normal force be greater than gravity? Let's say it was. Let's say the normal force was somehow 40 newtons. Then you would be flying. That doesn't really make sense. In an elevator, I guess it does. You could actually have that. We probably wouldn't call it normal force, though. We would say then the force of the motor is probably pulling the elevator up. So just so you know, normal force should never be greater than gravity. Because otherwise, I mean, if the table had more normal force than gravity did, things would start to float. Does that make sense?
Why is it 10 newtons and not 50 newtons?
The numbers I used to have were 20 newtons like up
Yeah, 20,
and 30 down. So like 20 up compensated by 30 down. The difference is
Cancel each other
10.
out then?
Yeah. Does that make sense?
It's not. You just add them together.
No, they're not scalars. Direction matters, right? Okay. I threw this diagram down here. Just like in the first unit, it's going to be very important that you keep track very diligently of all of the numbers you have, because you're going to get a lot of different values going on here. So here's some typical ones you could have. Forces due to gravity, applied force. So like if I actually actively start pushing something, then that would be an applied force. Sam, you mentioned an elevator a second ago. An elevator would have a normal force and an applied force. Does that make sense? Like if the elevator was standing still, the floor would be keeping you from plummeting through. If you then started to go up, that's because someone's probably like pulling on the cable, or like the motor is pulling the thing up. That's like a little different but similar. Oh, that makes sense. So you could have F, that's an A, I think. Does that show up better for you guys? Sorry. FA, applied force. Forces due to friction, forces due to tension, normal force, and net force. So make sure that you keep track of what forces you're talking about. Long story short, I don't ever want to see F equals 10 newtons. That's not good enough. Like, I need to know what kind of force we're talking about, because there's going to be a lot. Here's another example of like a picture I found. Here's a person pushing a box. Here's all the forces that are in play. First of all, gravity's pulling the box down. But unless the box is so heavy that the floor can't hold it, chances are the floor is actually pushing back up then. Does that make sense? So however big the gravitational force is, the normal force should be the same as it. Okay. Let's say the person is then pushing the box forward. See how I did like FAPP or FA? That's the applied force, so that's the person pushing the box forward. Well, what's this thing back here? Yeah, friction, right? What happens if this box is not moving? What would that mean? It means that the applied force that you're pushing with and the frictional force are the same. Does that make sense? Like, imagine that there's a really heavy boulder in front of me, and I'm trying to push, and it's not moving. I am actively pushing, am I not? Like, I'm actually trying, so I'm using a force, but why is the boulder not moving? Well, because there's so much friction between the boulder and the ground that really friction's pushing me back just as much. Let's say I want to actually get the boulder moving then. The applied force would then need to be bigger than the frictional force. Does that make sense?
So the frictional force is never less.
That's another good point here. Should the frictional force ever be greater than the applied force? And I would say, well, no, that doesn't make sense, because if somehow friction were greater than how you push, then the box would be going backwards.
Right.
But that doesn't really make sense, does it? The rock would not just randomly start rolling backwards on you. Unless there was a slope. And we'll get to those questions later, too. We'll do those later. Here's one more example, and then we'll actually do one that we'll do. Let's say there's a car weighing 10,000 newtons down. It's coasting on flat ground. Does it make sense to have a normal force of 10,000 newtons up?
It's not falling or flying.
Does that make sense? I mean, if somehow the normal force were higher, that wouldn't make sense. The car would then start flying. And if the normal force were less than the weight of the car, then the car would be crashing through the pavement, so that doesn't make sense either. Let's say there's air resistance of 2,500 newtons backwards. So that would be like an arrow going backwards here. And there's friction on the tires of 500 newtons backwards. As this diagram is currently shown, what should this car be doing then? Going backwards doesn't really make sense though, does it? Chances are I missed something here. There probably needs to be an applied force going forward, right? Like the motor of the car would be giving an applied force trying to go forward. And I don't know how many units the car's motor is working at, but I know what it needs to be greater than. Well, it's going to need to be bigger than the friction of the tires plus the resistance of air resistance. So it needs to be at least 3,000, right? Like if you don't have a force of at least 3,000 newtons, your car is not going forward. Does that make sense?
If it was just at 3,000, would it not be moving?
Yes.
Okay.
Yeah, at this point here. Or at the very least, its velocity would not change, but we'll get to that concept later. For right now, it'd be good to say, yeah, if we don't have at least 3,000 newtons, the car wouldn't be able to move forward. Okay.
So, it says like it has 10,000 newtons down, 10,000 newtons up, a normal force.
Yeah.
Is that just kind of how everything's gonna be if it's like on ground?
It's going to be the same. Yeah. Yeah, does that make sense?
Like just staying still?
Yeah, because like as this thing sits on the ground here, whatever's pulling it down better pull it up, right? Because if all of a sudden like it were to then crash and fall down through, then obviously the normal force, like maybe the pavement, there's a sinkhole in the pavement all of a sudden, and now you can start crashing through. I kind of envision like you ever see that TV commercial where like there's a guy in a bathtub in the top floor, and then like the bathtub crashes through the floor? I always think of that because then I think, well, now the normal force of the floor was obviously not enough to prevent the bathtub from crashing through. You ever seen that commercial, or am I crazy? You seen the commercial? Okay, you get the concept. Okay. Let's do an example then. So here's something I might ask of you then. Why don't I give you 30 seconds to read it first before we start? Like always, it's going to be a word problem, right? So you got two dogs pulling a sled. Dog A is slightly stronger than dog B. Apparently dog A is the alpha dog. Dog B is the beta dog. I don't know. So one dog is stronger than the other. There's also friction. So friction would, in theory, be pulling the sled backwards. And the driver also tries to pull the sled backwards. That makes sense so far? So a good way of solving a question like this is to actually draw a diagram. I don't need you to actually draw a sled. I'm not nearly artistic enough. Typically, a free body diagram involves a box. So the box is a sled. If you want to draw a sled, feel free, but like physicists are usually not artists. So don't worry about being artistic. There is one force going forward. One of the applied forces is a dog pulling at 200 newtons. There is a second applied force, 150 newtons. Why did I draw one line longer than the other? Yeah, one's stronger than the other, right? Friction is going backwards at 60 newtons. So that would be force of friction. And then the driver is trying to slow down the sled. I guess that could be another applied force at 100 newtons. Is the sled going to keep going forward? Yeah, how much total forward force is there? It's almost like you could do this. There's 200 newtons, plus there's 100 newtons, but then you got to subtract 60 newtons and subtract 100. Did I screw up? This is 150. Sorry. So what's that? 350 minus 160? 190? 190? So you could say that the net force on the sled is 190 newtons. Don't forget the unit though, forward. Because it's still moving forward. Sean?
Is there a way we would convert that to meters per second?
No, because these units aren't quite the same sort of thing. Like newtons is a measure of how much force there is. I kind of skipped that. Have you guys worked with newtons before in grade 10? Okay, sorry, I missed that then. A newton is a measure of strength. So like, you guys ever seen the movie where like I always think of Rocky IV where he's like punching that thing and it tells like how strong he can punch? Anybody ever seen that movie? Maybe. Anyways, it's a unit of like how strong something is. That's what newtons are. So this doesn't actually tell us anything about speed or distance. All it tells us is like with what strength is it pushing or pulling. Does that make sense, Sean? So kind of different units. Did that make sense? Okay. Because here's a more typical example. Your car gets stuck in a snowdrift. In order to get it out though, rather than pulling forward or backwards, what happens if things start getting pulled on angles? I don't know. All that angle stuff that we did in the last unit, it's not ever going away, just so you guys know. Because real life world stuff goes in north, south, east, west, up and down. So all of that trigonometry, we're still using that always. So I already gave you a bit of a diagram here. Friction is going to try to pull the car back west at 40 newtons. So that's a unit of strength. Whereas this guy right here can pull at 75 newtons, and this guy here can pull at 68 newtons. You guys see the issue here though is that they're not pulling like straight anymore. They're kind of pulling at an angle. Does that make sense? So we're going to have to do what we did in the last unit. We're going to have to make some triangles here. So I'm just going to make some triangles here. Here's one triangle. This would be the 75 newtons. This would be the 15 degrees. And I could look for the FY1, and I could find the FX1. Does that make sense? That would basically be this triangle right here. And I could also find another triangle here in green, which would be 68 newtons with an FX2 and an FY2, with that guy being 20 degrees. Does that make sense what I'm doing here? I've got to break up a hypotenuse value into actual XY values. Anybody want breakfast? Looks like we got oranges,
Yogurt and
3 juice boxes. I'll have a juice box if anyone else jumps then. Thank you.
Yeah.
Okay. So let's find the y and x components then of these two guys' forces. So how would you find this guy right here, Fy1?
Um, no, I mean,
Sine. Yeah. Sine of 15 degrees would be the opposite over the hypotenuse. So 75 times sine of 15 would be the Fy1. My calculator nearby again? Grab that.
8.965.
What'd you get, Nicole?
2.9658.
Are you in radians by chance?
Oh, never mind, I said decimal.
I got 19.4. Okay. So 19.41 newtons is your, what was that, Fy1?
yeah.
So if I wanted to find Fx1, then it would be 75 cosine of 15 degrees. Which I got 72.4.
Yeah.
Let me just talk about that for a second. Go back up to my diagram. How strong is person 1 pulling on the rope? Well, he's actually pulling with 75 newtons. But is all of that 75 newtons going in a useful direction? I'd say, well, no. 19.41 newtons is actually pulling the car kind of north, if that makes sense. That doesn't help because we need to pull it out of the rut the other way. So of that 75 newtons, there are 72.4 newtons that are actually going the way we want them to. Does that make sense? So now do the exact same thing for the other guy. The other guy is pulling kind of west, kind of south, east and south. So what would we do here? If I did 68 sine of 20, that would be the opposite. So that would be Fy2. And if I did 68 cosine of 20, that would be Fx2. Does that make sense what I'm doing? Okay.
Why is it FX on the bottom of the last one? Is it like,
Oh, sorry, you're right. That should have been Fx1. Thank you. Good catch. This guy right here you're suggesting. That's the one I did wrong. .68 sine 20. I got 23.3. And 63.9.
How do you know, how do you know when to put like the number in front of it?
Because I'm kind of shortening it up here. It used to be like sine of a number was like, say, opposite over hypotenuse. And since we know the hypotenuse, I'm just timesing the hypotenuse up. Always. Because like it's always going to do that. If you wanted to show every single step, I'm fine with that. But I'm kind of simplifying it to the last step here. Okay, I'm going to redraw my diagram then, if that's okay by you, because that first one up there is a little messy. Here's what we have then. You have your car, which I'm just going to use as a box. And here are all the forces acting on that car now. Backwards is the force of friction, and it was, I believe, 40 newtons. Does that make sense? Now, one of the guys was pulling in this direction here, and I've got a 72.4 as Fx1. The other guy was pulling in this direction, as fx2, and he was going 63.9. This guy would kind of move the car slightly downwards at, what was it, 23.3? That would be fy2. And this guy was pulling the car slightly upwards at 1941. Does that make sense how I've kind of redone my diagram now? And rather than do things on an angle, I'm now working in either left or right or up or down.
You just have to do all that stuff before to make.
Have to do all that stuff before to figure out the x and y directions. Does that make sense?
Okay.
Again, it's going to be very important to keep track. I don't care whether you call it fx1 or fa1 or fax. Like, I don't care what subscripts you use, but you're going to have to keep track of all of them because there's going to be a lot of numbers just everywhere. So organization is very important.
So now you like subtract and
Yeah, now we subtract and add. How much total force is pulling the car forward? Well,
those two out again.
72.4 plus 63.9. But then we got to subtract off 40 because friction pulls back at 40. So you could almost say that the F net in the x direction, I got 96.3 newtons. Like forward. Does that make sense? So if I add this guy, and I add this guy, but I subtract this guy, there's a net force in the x direction pulling you at 96.3. Is the car just going to go forward though, or is it going to go like slightly cockeyed, either north or south? We should also find the y value, right? Because do you guys see how like this y force up here, this guy pulls him slightly up, I guess? I think that was north, actually. But this guy's a little bit more, right? So you could also find a F net in the y direction, which would be 23.3 minus 19.41. I got 389. I think I should change my directions actually, because it wasn't forward and down. It was, I think it was north, south, east, west actually. Let me just draw the arrow here. It would be north, south, east, west. So let me change all that. These guys are actually going east, and this would be getting pulled south. Okay, so the net in y was I took this 23.3, which was kind of pulling him slightly down, and I subtracted this 1941, which was pulling him slightly up. Does that make sense? So like you got these two guys pulling this way right here. Yes, the car is actually going to go that way, but it goes like that way, but it goes like slightly south. Does that make sense? Because like this guy right here pulling at 75 and this guy here at 68, since this guy's pulling out this direction, the car will actually go like that. Does that make sense? Are we done? Yeah, we're actually not really quite done because now I can draw it like this. The car, some force pulled it this way. Some force pulled it slightly south. The actual car itself is actually going to be going on a bit of an angle. We got to actually find a resultant and find that angle. Again, hopefully you guys are seeing there's a lot of similarities here to what we did last unit. Sean.
Would you use the final net force in the x direction for the, the y?
Yep. We've done this quite a few times now, haven't we? So find me the hypotenuse, because that's the actual strength the car is going in that direction, right? And then inverse tan to find me the angle it's going at.
Is this an easy question?
Do you want the honest truth?
Yes.
Yes. This will be easy for you after a while. Like, and don't get me wrong, there's a lot of numbers going on, but there weren't a lot of twists on this question. Like, this question was fairly straightforward. Does it make sense where I'm trying to really harp on you guys to make your work neat and organized? Make sure that you can keep track of where numbers go because there's going to be numbers everywhere. C squared is a squared plus b squared. So square root 96.3 newtons and 398 newtons. Anybody get a hypotenuse value? 96.4? Okay. Depends on how many sig digs you kept. I should point out actually, I didn't penalize very often, if at all, for doing sig digs wrong. I'm going to start doing that though. So make sure when you get your final answer, which is here, we actually do sig digs properly. So 2. So 96 sig digs? 96 newtons? 96 sig digs. 96 newtons. And then we need to have an angle as well. When you inverse tan 389 over 96.3, I got 2.3 degrees. So then you could say, well, he was mostly going east, which is good because he had to get the car out of the rut, right? But the car went about 2.3 degrees to the south. What question is this similar to that we just did in the last unit? The airplane, boat kind of questions? That's what this unit is going to be all about, just so you guys know. Every question is going to be the airplane / boat kind of question.
Well, I didn't practice on that. Good.
You will get better at it, I promise, because that's what we're doing. A lot of trigonometry, right? All forces pull like exactly that way and exactly that way. Well, no. You could have a force that points that way and then kind of that way and one that goes that way and that way. And you're going to have to break things up into X and Y directions everywhere. Does that make sense? Okay, go take a 5-minute break here. Thanks, so. Here's a pretty typical example of a question. It's the same kind of question, believe it or not. It's going to use the exact same skills we've used before, but there's a twist. There's something new. I mean, that's what makes it a problem. We haven't solved one quite like this one before. One of the major issues to this question is I'm actually only going to give you one number to work with. You get to know that the gravitational force on this sign is 254 newtons. That's all you get to know. So this sign is being pulled down by a force of gravity of 254 newtons. My question is then, how much tension is there in this rope holding the sign to the one wall? And how much tension is there in this rope right here holding the sign like up and down? Do you guys get the concept here? One of the ropes is kind of half holding the sign up, and then this rope right here is preventing the sign from like swinging away from the building. Does that make sense? Well, let's start with a free body diagram then. What forces do we have actually acting on this thing? I'm just going to redo my diagram here. So this is the sign. Gravity's pulling it down. Does that make sense? What's holding it up then? Well, yeah, I guess maybe let's not call it normal force though, because normal force would be like the force that is like perpendicular on a surface. It's the tension in the one rope that's holding it up. But this rope right here, don't draw this, but this rope is going off at an angle. What could we do rather than draw it at an angle?
Draw it up and then draw another one going that way.
That'll work. So rather than drawing this one that I've drawn right here, let's break this one up into, there is some tension, let's go force tension in the Y direction from rope number 1, however you want to keep track of this. And there is also some tension in the X direction from rope number 1. Does that make sense?
Better explain it the other way.
Well, this rope right here you could almost break it up into some of it gets pulled this way and some of it gets pulled that way. But maybe to answer Haley's question then, how is the rope not moving this way?
The rope.
Yeah, the other rope that's holding it to the building, you could almost say that this is FT2. Do we have to break that guy up into an X and Y?
No.
We probably don't need to, do we? Is this rope, is this sign moving? Shouldn't be. Hopefully not. So here's what that means then. However much gravity is, this tension in the Y direction better be the exact same. Does that make sense? And however much force this rope pulls back to the wall, this rope better be pulling out as well. Does that make sense? Well, I only know one number though. I know what gravity is. I know gravity is 245 newtons. But I have an angle. I also know then that the force tension Y1, a lot of subscripts there, wouldn't that also be 245 newtons? Because it's not moving, right? If those two numbers weren't the same, either the sign would be falling or it'd be floating, like up. That doesn't make sense either, right? So hopefully the tension in the rope, if I go back up to my diagram here, this force tension in the Y direction, this force tension in the X direction, this thing holding it up better be the same as this guy pulling it back down. So that means that this guy right here is 245 newtons. Okay, if this angle right here is 55 degrees, is there an angle inside my triangle I can use?
Yeah.
What's this guy gonna be? Yeah, it'll be 35 degrees. So the Y component of this rope is 245 newtons, but I want to find the actual hypotenuse value here. So would it make sense then to say that the, let's see, that'll be the cosine of 35 degrees is normally the adjacent over the hypotenuse? Which one's the adjacent then? The 245, yeah. Let me write this out in stages though. This will be the FTY1. And then the hypotenuse will be the actual tension we're looking for. That's this guy here. So cosine of 35 degrees will be 245 over the tension I'm looking for. How do I solve this then? Cos 35, yeah. So to find the tension, like to find the actual hypotenuse, it's going to be 245 divided by cos 35. I got 299. So that means that this guy is at 299 newtons right here. So at the angle it's at, it's pulling at 299 newtons. Some of that force tension is pulling up at 245 newtons, but some of it is pulling outward. Could we then calculate the, I need more room here almost. Could we calculate the FTX one? You could use tan, you could use, you could almost use any value you wanted, couldn't you? That'll work too. You could use Pythagoras' theorem. I'll use tan. I'm kind of running out of room here. I'll go down here. If I did tan of 35 degrees, that would be the opposite over the adjacent. The opposite then would be F tension X over adjacent would have been F tension Y. Although I knew F tension Y, didn't I? That was the 245. So tan of 35 degrees would equal the F tension X over 245 newtons. Tan 35 times 245. I got 171.55. Did anybody try using like either Pythagoras' theorem or sine or something? Okay, so the only difference there will be just how many sig digs you probably kept, right? So, based on sig digs, how many sig digs do I even get? 3? I got 172 newtons then. So, if you are using a rounded value, just make sure you use every single decimal number you can. Does that make sense? Okay. So that means that this value right here is 172 newtons. Sean?
Did you add that to the FTX1? The string that's holding
The thing this way?
yeah, so did you add that to that?
To this guy right here? Well, that's what that guy will be. Does that make sense? If this string is pulling out at 172 newtons, then this guy right here is also pulling in at 172 newtons. Does that make sense? Because if the sign was stationary, however much force is pulling the sign away from the wall, the string that's keeping it attached to the wall should have the exact same force.
On this diagram you drew, which one is the 299?
We don't really have that one on this guy here, because the 299 would be like, if I didn't draw this guy with an XY component, if I got rid of that, it would be like the actual, like, does that make sense? Like the actual hypotenuse. So just to make sure I've summarized it here. Gravity pulls this guy down at 245. Therefore, the Y component of this string better also be 245. Using some trigonometry, we can find the actual tension in the string as 299. And we can also find the X component of the string as 172. In order to make sure that the sign does stay stationary, if this guy pulls out at 172, this string better be pulling back in at also 172.
I mean, so I have a question. What if it was like a vehicle moving forward?
Okay.
And you calculate that other one in the X direction?
That would be a little trickier here because a vehicle moving forward would probably have a net force and applied force. This one was solvable because this thing should be stationary.
Okay.
Does that make sense?
So
So, I mean, it is doable in the right context here, but like, because this thing is stationary, this force better be the same as this force. If it was moving, I would have to then tell you with what force it was moving forward.
Okay.
Does that make sense? You'd have to have that information, otherwise you couldn't figure it out.
Okay.
That's actually all I wanted. We wanted the tension on each rope. So this was the tension on rope number 1. And this guy right here was the tension on rope number 2.
And again, it's stationary, so you don't need a direction or.
Well, I guess we could throw a direction. This guy's tension would be going... I guess we should probably give a direction. We could go like up, down, right, left. Okay, so like this guy's tension here would be at 172 newtons right, I guess you could say. This guy right here, it's gonna be a little trickier. We'd have to like go with a direction. Let's see. Since the tension is like pulling it back into the wall, would it make sense to call this angle here 55 degrees? That makes sense, because like if this guy's 35 here and that's 90, that's 55. So then you could say this would be going left 55 degrees up. You're originally going left, then you're swinging it to the up direction 55. Does that make sense? Sean?
Will we be doing questions where like the sign is going back and forth?
I could. I don't want to like say no to that. This question wouldn't have been solvable though under these parameters here if it was actually like swaying in the wind. Does that make sense? But I mean, it is possible if I give you the right context. So. Questions? Okay, brief summary then, and I guess we've got 15 minutes left. The skills we're going to use in this unit, if you haven't noticed already, a lot similar to some of the skills we had last unit. You got to use a lot of trigonometry. I mean, life is messy. Things go at different angles. Not everything goes exactly north and south, right? Sometimes it goes, this one goes north, but that one goes kind of kind of half off, cockeyed, right? Does that make sense? So the best way of solving these questions, you've got to break everything up into an x and a y component. Does that make sense? And so you got to get pretty good at doing all of that trigonometry type stuff where you do x1, y1, x2, y2. I don't care what uses your labels, by the way. So like if you want to call it ftx1, that's fine. But you've got to do something to keep organized. Does that make sense? Because you can't just say force equals 15. Because like I will have no idea what force you're talking about. That makes sense? Like organization is very, very important. Because hopefully you figure this out. There's numbers everywhere. Okay. Any questions, guys? Okay. One last thought, then we can take off. I don't have an assignment for you to work on. I mean, we barely just started. Usually at the beginning of the unit, I just give you some textbook questions. They're not due by any means, but it wouldn't hurt to practice one or two of them. So I pulled a couple out of your book, 2, 3, 5 to 8. Maybe try one or two of those ones.